light behaves like a particle and a wave. And an example of the wave behavior of light is interference, reflection, refraction, and so on. And an example of the particle behavior is the photoelectric effect. Now, light is essentially an electromagnetic wave that can propagate through a vacuum. So the speed of light through a vacuum is around 3 by 10 to the 8 meters per second. And other waves, like a ripple through water for example, need a medium to propagate. And a sound wave is another example of a wave that requires a medium to propagate. So essentially a wave is a disturbance that transfers energy without transferring matter between 2 points. Now light waves are transverse, so they comprise electric and magnetic fields, and these vary with time, and they oscillate perpendicular to the direction of propagation of the wave. Now consider this light source. So the waves that propagate away from the light source are spherical in 3 dimensions. But if we consider this plane, we can see that the circles represent the position of the wavefront away from the light source. And a wavefront comprises photons that oscillate in the same phase and at the same frequency. So you can imagine these photons oscillating back and forth out of the screen. So on this wavefront moving outwards, the photons are fully out of the screen. And if we trace out the wavefront based on the oscillations of the photons in and out of the screen, it looks something like this. And this point where the photons are out of the screen is called the crest. And between these positions of the wavefront, we have the trough. And we draw light rays emanating from the light source. And these rays are perpendicular to the wavefront at each of those points. So they're pointing in the direction that the light wave is traveling, in each of those directions. So another example here is this ripple in a pond. So we can observe the movement of the wavefront, where the particles of water are in a maximum upward direction, and in between, the water particles are in a downward direction. So you see like a sinusoidal oscillation as you move away from where the rock was dropped. And we'll look at waves in more detail in the next unit, but for now, we're going to use light rays to determine the behavior of light, which is essentially geometric optics, where we neglect the wave nature of light. So these rays interact with surfaces, and parts of these rays get refracted or bent as they travel through a surface, and some of it gets reflected from the surface. So note that rays are not sufficient to understand the spread of light, so the wave nature of light needs to be studied, where we have interference between waves and diffraction, which we'll look at later on. Now visible light, or the light that we can see, makes up a small part of the electromagnetic spectrum. So this comprises radio waves, which have the lowest frequency, up to gamma rays with the highest frequency. So as we can see, frequency increases as we go up the spectrum. So for example, you may have a light wave that oscillates like this, whereas at the lower frequency it may oscillate like this. So radio waves have a lower energy than gamma rays. So you have a larger wavelength compared to the upper part of the spectrum. And we're going to use ray diagrams to predict the path of light before and after it interacts with matter. Light that is incident on a surface can be reflected. And the law of reflection states that the angle of incidence, being the angle between the incident ray and the normal to the surface, which is this angle over here, is equal to the angle of reflection. So that's the angle between its reflected ray and the normal to the surface at this point. And this can be proven using the Huygens-Fresnel principle, which states that every point on the wavefront is a source of spherical wavelets. And these secondary wavelets that emanate from these points mutually interfere with each other. So as they propagate, they end up being spherical themselves. So using this principle, we consider this light ray and the propagation of this wavefront to the surface. So when this wavefront hits the surface, it looks something like this. So when we're looking at a small part of the surface, compared to the distance from the light source, the further away the spherical wave is from the light source, the spherical wave appears more and more like a plane wave. And that's how we'll treat the wavefront. So as we said, the wavefront is perpendicular to the light ray, and at some point on the wavefront, we have a secondary wave emanating from this point, according to Huygens' principle, and the distance that this wavefront travels from this point is the speed of light multiplied by time t. And note that the speed of light is approximately equal to c in air also. Now after this incident wave w collides with the surface, it gets reflected. And the reflected wavefront is seen by this hemisphere above the surface. So the blue reflected ray is perpendicular to this wavefront. And this blue line here represents the reflected wavefront, which is tangent to this circle at this point. So by geometry, we can see that this angle is equal to the incident angle. So the angle that the ray makes with the normal to the surface is equal to the angle between the wavefront and the surface. And on this side, we denote the angle between the reflected wavefront and the surface as theta r. Now the time taken for this secondary wave to collide with this surface is the same as the time taken for the reflected primary wave to travel the same distance from this surface. So therefore, if the length of this reflected ray is ct, then these two edges are identical. And these two angles are also identical. So therefore we have two right angle triangles that have a common edge at this surface, and they have a common angle, and the other edge has the same length. So these two triangles are congruent. And that means that theta I is equal to theta r. And I'll leave it for you to show that theta r is the same as the angle between a reflected ray and the normal to the surface. And you can visualize that using basic geometry. Specular reflection is the reflection of light from a relatively smooth surface. So in this case, the normal to the surface is relatively constant. So therefore the angle of incidence, or the angle that the incident light ray makes with the normal, is equal to the angle of reflection, or the angle between a reflected light ray and the normal to the surface. Now on the other hand, diffuse reflection is the reflection of light from a rough surface. And this results in light being reflected in many different directions because the normal to the surface varies along its area. So for example, at this point, the normal to the surface may be in this direction, and therefore the angle of incidence being equal to the angle of reflection results in a reflected ray that points in this direction. Whereas at this point, the normal to the surface is in this direction, so the incident angle in this case is 0, and therefore the angle of reflection is 0. So the reflected ray points in that direction. And over here, the normal to the surface points upwards, so the angle of incidence being equal to the angle of reflection results in a light ray that gets reflected in this direction.